So this will be the last of the slides that's talking about what happens at plate boundaries and what kind of features we see created by plate tectonics. So let's talk first about continent-continent convergent. So where we left off was um, subduction zones, and here we can see a continent on the right and ocean crust on the left, but something is always on the other side of the ocean. And so if that plate, if that lithosphere has continental type crust on top, it is not going to be able to subduct. You'll notice on this picture, and if we go back to this previous picture, the plate that goes down is always ocean crust on top. And that's because the ocean crust is relatively thin, and its density and composition are much closer to the density and composition of the rest of the lithosphere, which is kind of the greenish part that's underneath here. So what happens if we have a situation like this, a subduction zone, and then a continent approaches from the other side? And so we can see in this top drawing up here, we have our continental shelf and the attachment there. Remember, if we go way, way back, this was one side of our original divergent margin. So now it's coming back and it's approaching this continent over here. It's not going to go down, and instead we get a major, major collision. Subduction, however, has stopped. So what does this look like? Well, this is actually a little simpler to talk about. We have high pressure convergence. If we look at this, we have subduction, partial melting, accretion. When we come over here, we don't have any of that. We just have high pressure convergence. We get folding, some very intense folding. We get reverse and thrust faulting. So that's the kind of faulting associated with convergence. We get shallow earthquakes, lots and lots of shallow earthquakes. And we also get regional metamorphism, which they show here in purple. So all that high pressure is going to fold and fault the rocks as well as metamorphose them and change them. And where do we see this occurring today? We see this occurring where India is crashing into the south side of Asia, and it's actually pushed its way in. You can see we have folding, pretty easy to see on the sides here on the left and on the right. And then right here in the middle, there is some intense folding, but this is currently the world's tallest mountain range as India continues to push into the south side of Asia, and that's the Himalayas right there. So that's what we see. But you'll notice that they do not have volcanoes because there's nothing going on here to trigger melting. So that is our continent-continent convergent margin. And that brings us to our third and final style of plate boundary, which is our transform margin. And we see transform margins primarily in two settings. Mid-ocean ridges occur on a curved surface. So what you might have noticed way back when we talked about mid-ocean ridges, and I might actually scroll back to a mid-ocean ridge slide right here that shows the Atlantic Ocean, you'll notice that the mid-ocean ridge is just not a solid line of ridge with rift in the middle. That mid-ocean ridge is typically offset by a little or a lot by all these faults that cut across it. These are our transform faults. And what's happening here is the divergence is occurring along a curved surface. The surface of the Earth, as you might know, is round. And when you pull things apart on a round surface, different parts will pull apart at different rates. And in order to accommodate that curved surface, you need to have these transform faults which offset the mid-ocean ridge. And so that's what we're seeing right here is a lot of small transform faults offsetting that divergent margin mid-ocean ridge. The other place where we see transform faults are just where one plate is sliding past the other. And so our best example of that is probably the San Andreas Fault. You can see it here on the lower right-hand side. It's a long fracture that runs along the surface of the Earth. In terms of the geologic features we find here, this is a relatively simple boundary. We see strike-slip faulting with a lot of shallow earthquakes, and that's primarily what we see. Now, because the rocks don't slide smoothly past each other, you get crumpling on either side, so we do get some small mountains associated with this. So you'll notice on either side of this fracture in the picture in the lower right, there are some small hills, or some people might call them small mountains. But that is what we see along a strike-slip boundary, really primarily strike-slip faulting, taking care of that transform motion. So let's take a close look at the San Andreas Fault. This is a section of the San Andreas Fault near San Francisco. So this is the San Francisco Bay right here. The Golden Gate and the Golden Gate Bridge are right there where I'm running the cursor. And you'll notice that this transform fault on the left is the Pacific Plate, and a small sliver of that is continental type crust. And then on the right-hand side is North America, and the relative motions are shown with those red arrows. What we're going to do on the next slide is kind of focus in on this area up here. This is called the Point Reyes Peninsula. You'll notice there's kind of a cleft associated with the San Andreas Fault zone right there. So let's take a look at that. There it is. You'll notice there's a little bay here, and there's a long, narrow bay right here. And we're going to focus in on this area right here. Last summer, I was there on a trip with my son. We drove up the Northern California coast, but we made sure to stop here at the San Andreas Fault and take a few pictures. And so that's what you're going to see next. This is what it looks like. You'll notice that there isn't a prominent crack in the ground. There's a little valley off to the right, but this is a place where in the great earthquake of 1906, a fence was offset by about 12 feet. So the way I'm standing is my left foot, which is the foot over here, is on the Pacific Plate. My right foot, which is uphill, is on the North American Plate, and the fault runs right between my legs. And you can see the offset fence was preserved by the property owner, and it's now part of a park. This is my son. Different view of the same location. Behind him is the North American Plate. In front of him is the Pacific Plate, and you can see the offset. And they even added some stairs to make it more convenient to go up there and take pictures like we took. So that is what a transform margin looks like if you go visit it. So now we're going to just wrap this talk up with just a few details, a couple things that are associated with plate tectonics that are kind of interesting and important to know. At convergent margins, we mentioned the idea of accretion and the accretionary wedge that occurs along a subduction zone. However, we can take this even a little bit farther, because any large chunk of material that does not go down into the subduction zone can be added to the overriding plate. And this is how continents form and grow larger. And there's some pictures in your book that show you this. But I wanted to show you on going across the bottom, the Paleozoic, geologically speaking, is over 250 million years ago. And what you can see in the western United States in the lower left-hand corner is that our part of North America included Idaho and Utah and Arizona, but doesn't include Washington State, Oregon, most of Nevada, and California. And you can see that over the course of about 300 million years, North America has slowly accumulated more and more material through accretion and has built out the continent, and that's how we now include the western states, Washington, Oregon, California, Nevada. And the picture in the upper right-hand corner of this slide shows you in different colors the ages of material kind of and when they were added. The earliest stuff that we added is in blue, and then stuff that was added after that is shown in green, red, and yellow. And so continents build out through continental accretion at subduction zones, and so that's how we get larger and larger continents. There's another set of drawings in your book that show you the development of the Caribbean Sea and some of the islands that are there. You can see if you go back 175 million years ago, South America and Africa are still attached, but South America and North America are not. They're actually rifting apart. You can see the Yucatan, which is now attached to Mexico, is kind of its own thing. As this area develops, a subduction zone is located along the western edge of the Americas, and you get some rifting there as well as things pull apart and some islands form. So we've got our nice little subduction zone there. North America is pulling away from South America, but at 84 million years ago, you can see this oceanic plateau, which is basically a thick chunk of crust that can't subduct, runs into our subduction zone and basically punches through that area between North America and South America. And as it punches through, a new subduction zone forms on the leading edge. There's some islands that form there. We have a transform margins on the two sides as this little piece of continent, we would call it a microplate, pushes its way through. And as it does, it results in the formation of, you'll notice, Cuba and the islands that we call the Lesser Antilles. That includes the island of Montserrat, which recently had to be evacuated because of the activity of its volcano. And you can also see that oceanic plateau ends up becoming Haiti and Puerto Rico. There's Cuba up there. And then once that microplate pushes its way through, a new subduction zone develops on the back side and forms what we refer to as the Isthmus of Panama, which then connects North and South America. So that kind of shows you what was happening in that area and how that relates to plate tectonics. And these faults are all still active, and the subduction zones are active as well. So we have volcanoes and lots of earthquakes in those areas. And so that's pretty much it for plate tectonics. There's a lot of cool information in the book. It really helps us understand the Earth and how it works. We'll leave you with this, with another comic, just like I started with a comic, talking about how slow the plates move. If you're confused by the names of all the plates and everything, he's poking fun at geologists by saying there's so many little microplates in all different ages that you can just replace them with dog breeds and you still sound like you know what you're talking about. So that will be the last slide for the last unit of the semester. And if you have any questions, please send me an email at the new email address I sent out to everybody via Blackboard, or post your questions in the Blackboard discussion.